Hello, this is a short video teaser for our paper Subcubic certificates for CFL Reachability. My name is Dmitry Chistikov. I'm at the University of Warwick in the UK, and we wrote this paper with Rupak Majumdar and Philipp Schepper. CFL reachability, or context-free language reachability, is a problem that probably needs no introduction to the popular community. It has multiple applications in computer science. CFL reachability was introduced more than 30 years ago by Dolev, Evan, and Karp. And this is a certain decision problem. So as input, it has a directed graph with labels, and let m be the number of vertices in this graph. So this problem is known to be solvable in polynomial time, and in particular in cubic time. And the best known algorithm so far is by Swaraj-Chowdhury, presented at Popple 14 years ago, which has running time n cube over log n. The best lower bounds for this problem are of the form n to the omega, where omega is the matrix multiplication exponent. You can think of omega as 2.4. It all started in 1974 with this paper by Leslie Valiant, a Turing Award winner. So Valiant proved in the 1970s that for the problem of recognition of context-free languages, there is a reduction from this problem to the problem of multiplying two matrices. It gives you an algorithm that lets you recognize context-free languages in less than cubic time. But this is a different problem. Swaraj-Chowdhury, when he presented an algorithm, a subcubic algorithm for CFL reachability, let me remind you that this algorithm has complexity n cube over log n, slightly better than n cube. He wrote that it is a hard open question whether all pairs CFL reachability can be reduced to Boolean matrix multiplication. Is there truly subcubic algorithm? This is a somewhat different question. One with running time n power 3 minus epsilon for some constant epsilon. The answer to this question is unknown. Can we obtain a lower bound for CFL reachability that would be stronger than n to the omega? How do we obtain in general lower bounds for problems like this? There is a whole theory of so-called fine-grained complexity with fine-grained reductions that establish conditional lower bounds within polynomial time. So this is a picture from a survey by Virginia Vasilevska-Williams 7 years ago. So there are multiple hypotheses and multiple reductions that show conditional hardness. And in principle, it would be very nice if we could show that the CFL reachability is hard for n cube. So, however, here is the summary of our main result that we show in this year's Popple. An appropriate reduction from SAT to CFL reachability would have significant consequences in circuit complexity. I'm simplifying away many things here, but here is the core idea. The idea is certificates. Given an instance of CFL reachability, I can use something called certificates to convince anyone whether a given instance is a yes instance or no instance. Importantly, the certificates are subcubic. In fact, they have quadratic size, and they can be verified in strongly subcubic time. And it implies, and I'll talk more about this in the main talk, that any appropriate reduction from satisfiability to CFL reachability, and this is really the main source of reductions for many of these fine-grained, for this fine-grained landscape. Any appropriate reduction like this would break so-called non-deterministic strong exponential time hypothesis. Basically, this would imply better than 2 to the m proof systems for tautology, and you can prove to other people whether a given unsatisfiable instance of SAT is really unsatisfiable. So this would be a breakthrough result. So that's why such reductions, such hardness lower bounds for CFL reachability are, we can say, unlikely. That's the summary of the paper, and I look forward to the conference.